So as Marco said, I'm Tim Randles. I'm from Los Alamos National Laboratory. I'm part of the HPC design group there. A couple guys who couldn't be here today. Reed Podorsky is actually the majority code author of Charliecloud. He's in our HPC environments group. And Michael Jennings, who's in our systems team. So he's the leader of the sysadmin group at Los Alamos HPC. So we're going to talk a little bit about, we're going to talk about Charliecloud, but we'll talk a little bit about some motivating factors, which I think everybody here understands. We've heard about them all day, but they inform our design goals. We'll talk a little bit about some basic container ingredients, and then what Charliecloud's approach is using those ingredients. And then adoption and resources that are around Charliecloud. I think everybody in the room knows why we want user-defined software stacks on our HPC systems. Software dependencies, unusual ones especially. Reed has a funny way of saying this. When you're running a large HPC center, we have over 20 clusters and 13 admins. When someone shows up and they want a new software stack that we haven't seen before for our traditional HPC workloads, MPI-based, tightly coupled simulations, we don't know if you're the next great innovator in computing or a total crackpot. So we have to really think hard about what we're going to spend our time supporting and installing, and what we need to be able to put out there. But if we can give someone a user-defined software, that user bring it, we can maybe not worry quite as much about the distinction of where you are on the innovator timeline, or innovator spectrum, I guess. So also, portability of environments. So we've heard a lot today about portability between HPC and cloud resources. Another dimension of this portability is the environment that the user sees. It's not often that you have the exact same environment on your development workstation that you do on your HPC resource. So the portability here is a portability of the exact same environment that the user is comfortable using, he's developed in, he works in every day, all the way out to our HPC systems. At Los Alamos, we use a Linux distribution called TOS, which is TriLab operating system. It's a Red Hat derived distribution, but if I look around the room, there are a few folks who may have Linux on their desktops, but chances are you don't. You're using a Mac. In fact, there's an awful lot of Macs in here. Or you're using a Windows environment or something else. The portability of the environment, being able to work in a virtual machine with Ubuntu or something like this, and then carry that environment up and run it on our HPC resources, is something that our code teams actually are asking for. And a consistent environment. So the first one here, validated, is an important one. I come from the physics community. I got into HPC about a decade ago. But we have quite a few, where I was at before, folks working with the LHC. And we know what the environment's like when locally you're not equipped, or the research team isn't equipped to support scientific Linux on a desktop or a closet cluster, yet that's a requirement for publishing. The fact that the analysis environment has been accepted by the research community is often a support challenge at a local organization. So if you have the way to pick up your analysis environment all the way down to something approaching an OS level and put it onto one of our HPC resources, you should be able to take advantage of the scale of hardware that we have using a software stack that we don't support. Usability actually goes back to the portability argument and making people comfortable with what's available for their software. So there's some disadvantages here that people have talked about today: missing functionality, high-speed networks, accelerators, file systems. These are all things that in HPC we've worked hard at over decades to maybe not perfect, but at least make highly available, good performing parallel file systems. We don't want our container runtime to abstract these away from your job. The reason you want to run on the HPC resources are the reasons that HPC is special, and it's largely around these three topics here. So if we can give you a way to bring in your software stack without breaking what's special about our HPC systems, you should get more utility out of it. And performance, these are all go back to performance. But the technologies that existed prior to Linux containers were largely virtual machines, and there's all sorts of opportunities for overhead there. So from these advantages and disadvantages, we derive 3 design goals: a standard reproducible workflow. We want to work well on existing resources, and we want to be very, very simple. So a little more about these. Standard reproducible workflow. Tinker till it's ready and then freeze is largely the way our code teams have worked on bare metal for the last 25 years. They tinker till it works, they get good performance, they start running their application, and then someone like me, an admin, comes along and says, I have to do a software upgrade, and suddenly we're getting trouble tickets saying my software doesn't work anymore, or it's slow, what did you do to, excuse me, what did you do to the system to break it? So being able to encapsulate your environment into a container should disconnect your applications, should disconnect the entire environment that your application needs to run without destroying the fact that it actually works well. Standard, we wanted a standard workflow to reduce training and development costs and to increase skill portability. I sit on a lot of hiring committees at Los Alamos. It's really hard to find people coming out of school that know HPC. They may have some parallel programming experience, they may have some MPI experience, but they don't have deep experience in introducing a new technology like containers, and then saying that we have our own bespoke containerized environment even narrows that field even more. So we want to reduce training development costs and skills portability, so we built Charliecloud is nothing more than a lightweight runtime, and we rely on de facto standards today, such as Docker, to handle building our images. We want it to be reproducible. Once again, the Docker ecosystem provides that reproducibility through Docker files. We want to work well in existing resources. We're good at what we do. Let's not re-implement and re-optimize. So resource management solved. We've got all sorts of resource managers. File systems, we've got scalable, high-performance parallel file systems. We can debate stability of those some other time, but you want fast, you've got fast. We have high-speed interconnects, InfiniBand and OPA. In particular, high-speed interconnect, virtual machines, I/O tends to be a bottleneck, has in the past. There are technologies that get you around that, such as SRIOV or PCI pass-through. SRIOV is now more supported than it used to be, but it tends to be fragile, I think. PCI pass-through is a little bit of a security problem. If you're going to give someone PCI pass-through, it gives them the actual ability to do whatever they want with that hardware inside of a virtual machine. So we don't want to abstract this stuff away. And we want to be very, very simple. This saves costs, particularly in security, where Charliecloud's entire code base is just over 1,000 lines of code. A lot of it's C, some of it's shell scripts, but it's small enough that a reasonably competent security auditor can go through and actually audit this in a day. And we adhere to the Unix philosophy, make each program do one thing well. So container ingredients, there's more than just this, but these are the ones that you're likely to have heard of. Linux namespaces, which they're data structures in the kernel that just give a process a view of the system. There are 7 of them. We'll get into them in a second, but well, why don't we just get into them? Charliecloud only uses user amount. The first 6 on here are all privileged namespaces. The 7th that came along in 2013 and has been largely stable since 2015 is user. You can instantiate any of the privileged namespaces at the same time as user without having privileges. So if you start a user namespace by calling one of these, well, the first 2, system calls, unshare or clone, you say, I want a user namespace, and you can pick any of the privileged ones that you want at that time and only at that time, and the kernel won't let you do it again. So we only use user and mount namespaces. There's a bunch of reasons why we don't want to actually use these in our lightweight runtime. Most of them having to do with, once again, not trying to abstract away what makes our HPC system special. There's other items like IPC and PID namespace. If we abstract those away, it's awful hard for a user to SSH into a machine and then attach a debugger, for instance, or a profiler to their code while it's running. And we didn't want to go to the added complexity of trying to spin up a custom SSH daemon inside of this namespace just to get to your program that's actually running on the system. We just want you to see it when you get on the system. There are also C groups or control groups. This limits resource consumption per process on a Linux host. We don't mess with those. There are other mechanisms that are much better at handling those than having us re-implement them for you, such as your resource manager. We'll handle those things. So Charliecloud takes a hybrid approach. Image building and sharing goes in a sandbox. And I say for now, it's a sandbox today because we want our users to use Docker. Docker set UID. Docker has a whole host of other security problems we've heard about today, lots of CVEs and stuff. I like Docker for development and building your image, but I don't want you to use it on my machine. I want you to use it on your own. We say for now because there are a number of unprivileged tools coming down the pipe that lets you use a Docker file to build your image that's Docker compliant without actually using Docker to do it. So one of these is IMG from Jess Frizzell. It's written in Go, I believe. We've played some with that. We also are looking at Builda from Red Hat. Builda requires a newer version of shadow utils than Red Hat currently provides, which is unfortunate for us, but it also is causing some consternation from the Builda developer who actually works for Red Hat, saying, my tool's great, it does unprivileged builds of Docker files, and you won't ship the package that my customers need to use it. But we are looking at it. So I think this will fall away soon. So what we tell our users, though, is use Docker for image building, but anything else that can produce a file system tree. Charliecloud doesn't care. All it wants at the end of the day is a file system tree. So during the UDocker talk, the ability of UDocker to pull from a Docker hub using the Docker API, flatten that image, protect all the white spacing and permissions into some tree, Charliecloud should be able to run against that. NASA Ames actually is using Charliecloud on their Pleiades cluster. They have an NFS directory structure where they use fakeroot to install whatever operating system a user wants into this directory structure and then install the app inside of it, and they just leave it there, mounted on all the cluster, and say, whenever you want to use this software stack, use Charliecloud's runtime and point it at this directory, and voila, you're in that. And that's the running images with our own unprivileged runtime. It is your own because it's a user program. We need the user and mount namespaces. This used to have some caveats here about what distros had the right kernel. Red Hat 7.6, I believe, finally ships with user namespaces enabled. Ubuntu's been doing it since, I think, 14.04. I know for sure 16.04. But all the distros have the right kernel and the right namespace support to use Charliecloud. It is a user program. Admins don't do anything. So when I used to give this talk, I'd say to the admins, this is a warning. Any user can just go do this on your system whether you want them to or not. Now Red Hat has put some hooks into the kernel through the proc file system so that you can disable or configure the number of any namespace that you want users to be able to instantiate. But on some kernels distributed by some vendors, that interface doesn't exist. There's nothing an admin can do to stop you from using Charliecloud to run your container or from you reading the Charliecloud source code and writing your own implementation of this. Or, if I go back a couple, there's actually an unshare command line tool that's nothing more than a wrapper around the unshare system call to do this exact same thing again. But admins don't need to do anything. All Charliecloud uses are mount and user namespaces. We're not set UID. You already make the bargain with the kernel developers when you boot the machine that you trust the kernel security. That's all we're taking advantage of with Charliecloud. We didn't want to write our own set UID binary. You don't want to trust me to cross security domains in your kernel. So we've left it up to the experts that actually write the kernel to get the security right. You already do this every day. If you let a user on a system, you're trusting the kernel to do the right thing. So it's lightweight. Charliecloud is lightweight. There's no complex installation. There's no configuration required. I looked before I started today. We're around 1,300 lines of code now. Most of the growth, this used to say 800, is around shell scripts that do some helper functions. We'll go back to this in a second. Unprivileged, any user can run it. If you install util Linux on your systems, and you do, I think, unless you go back and remove the unshare command line tool, the wrapper around the unshare system call, users can do basically what Charliecloud does in a shell script. There's no HPC Center admin intervention required. Works on all up-to-date Linux distributions. It's hardware agnostic. We've tested it. We have all 3 of these architectures running inside of the TriLab complex in the DOE. We support all of these, although it doesn't require much Charliecloud support. The kernel has it. It's not on here because it's not official, so to speak. I've actually hacked Charliecloud to work on an Android phone. The Linux kernel data structures, once again, are there's in the kernel, so it just works. We support InfiniBand and OmniPath. Once again, that's a little bit of a conceit, the same way with NVIDIA GPUs, because we don't do anything to hide these from you. We have some helper functions that make it easier to use these, however. There's a Charliecloud command called ch_from_host, and you can say ch_from_host -- NVIDIA and point it at your image, and it will use the NVIDIA CLI tool to figure out which libraries are needed for the CUDA or OpenCL application, or really for the hardware on your system, and we'll inject those into the image, into something in the containers LD library path, what's configured there, and actually run LD config. It just works. So if I have more time, I often do a demo with TensorFlow. We'll take a TensorFlow Docker file. I'll download it from Docker Hub. I'll throw it on one of our crays. No GPUs on our cray. We'll throw it on the cray. We'll run it with Charliecloud. It just works. Take the exact same image. We'll move it over to one of our GPU clusters. It's just a generic x86 white box system for all intents and purposes. We'll run this image. It just works. We'll run the ch_from_host to say, put my NVIDIA libraries into the image. It'll drop them into the image. We'll run it again. We'll run through the training data set, and it says, hey, look, I found GPUs. It just works. So I think the portability is certainly there in the container environment. I think performant portability is close at hand. I mentioned the interfaces, InfiniBand and OPA. MPI. Everybody has questions about how does MPI work. The Shifter guys really solved this, and we work closely with Shane Cannon and Doug Jacobson at NERSC to share ideas in our runtime. NERSC developed Shifter to run on Cori, which is a cray system. It uses cray pitch. It has their own proprietary interconnect. It's called Aries in this case. They figured out a way to inject, to build your container using open source mpitch, and then when you import the image into Shifter and run it, they take the cray libraries, they insert that into your image, they do a little patch elf trick so that the loader can find the cray libraries, and then you run at native speeds. We've incorporated that same thing with their help into Charliecloud using the same from_host command. So you can say ch_from_host -- MPI, and your OpenMPitch compiled container will work fine with cray pitch on one of our cray platforms. One of the nice things about working at Los Alamos is we have OpenMPI developers there. We're making improvements and having MPI work in containers, but we're not making those improvements to Charliecloud. We're actually going back into OpenMPI and filing bug reports to say, you know, this stuff doesn't work in certain ways with namespaces in a Linux kernel. So hopefully you all benefit from this. A quick one that I like to talk about is the fact that the byte transport layer inside of OpenMPI changes based on message size. So we used to do a little hello world with Charliecloud, and hey, look, it just works fine. Then people start running real applications, and it's like, you know, my application runs for like 20 minutes and then it breaks. And we don't know why. Well, it turns out that the cross-memory attached functionality in the Linux kernel is disabled if you're using user namespaces. So we've fed back into the OpenMPI developers this knowledge, which they've then gone and fixed in OpenMPI to say, okay, if I'm running in Linux namespaces, if I'm in a user namespace, I can detect this. Don't enable CMA. We also did put a little bit of functionality in Charliecloud, which is something called join. So you can run your MPI application with Charliecloud, and if you say -- join to the Charliecloud runtime, and you're going to run, let's say, 32 ranks, or 32 MPI ranks It's a race. So you srun your application, you launch your Charliecloud container, the Charliecloud sets up the namespaces required and then exits after it launches your application. It uses mutex and shared memory to say, I'm setting up the namespaces, wait on me, I'm done, here it is, and all the other ones that come up actually join that namespace. We don't keep running more containers. We just start more processes than the one you've already got running. I did mention srun. So earlier we saw a slide where someone had MPI run and then the container runtime and it didn't work. If the MPI in your container is different than the MPI outside of your container, you'll get warnings about this. We use, at Los Alamos, we compile Slurm with PMI support. If you use PMI to wire up your MPI job, I don't care what version of MPI you have installed on your machine. If you type srun chrun, it uses all the MPI inside of your container and just works. Available today, yeah. So Charliecloud versus the design goals, standard reproducible workflow. Yes, because we're using tools that we don't have to support that are standard and reproducible and the rest of the world uses, not just the HPC folks. It works well in existing resources. There's no persistent runtime. Charliecloud sets up namespaces and launches your application in that namespaces and exits. We don't try to abstract away what makes our HPC system special. Be very simple. I encourage you to clone us off of GitHub and take a look at the code. It's very well documented. If you want to learn how Linux namespaces work and the tricks we use, there's actually a subtle trick in there about how the kernel treats the root of the file system tree that Reed uncovered while he was developing Charliecloud. Go take a look at it. It is indeed very simple. So Charliecloud adoption, lots of people in the industry have talked to us and are using Charliecloud. Academia, lots of labs, and there are a few resources. I don't know where I'm at on time.